Good morning, good afternoon, good evening, and welcome to AI for Good. We hope that you, your family members, your friends, and your colleagues are all keeping healthy and safe. My name is Fred Werner from the ITU, the International Telecommunication Union, and it's a privilege for me to introduce today's webinar. Now, the ITU is the United Nations Agency for Information and Communication Technologies, and we're also the organizers of AI for Good, in partnership with 38 UN sister agencies, X Prize Foundation, ACM, and co-convened with Switzerland. And the goal of AI for Good is to identify practical applications of AI to advance the Sustainable Development Goals and help to scale those solutions for global impact. And today's session is a perfect example of that, as we're going to look at how AI can help to optimize and help to accelerate the development of nuclear energy technologies. Now, before I introduce today's moderator, I'd like to go over a few housekeeping issues. First of all, your microphone has been disabled, so please use the chat and Q&A functions if you wish to communicate. It's the role of the moderator to identify questions and ask these questions to the speakers and panelists, and we're counting on your active participation to have a very interactive session. And speaking of being interactive, I have a first challenge for you. Can you please let us know where you're connecting from? Simply use the chat function and make sure it's marked chat to everyone and type in where you're coming from, which country, city, company, university, whatever. Here, I'll go first. Geneva, Switzerland. Okay, Argentina, Canada, Mexico, Liverpool, Netherlands, India, Palestine, Cairo, Philadelphia, Istanbul, Mumbai. Wow, they're coming so quick I can't even read them. And that's great. We truly have a global audience with us here today. So without further ado, I'd like to introduce the organizer of today's session. His name is Chirayu Batra, and he's a project officer from IAEA. And I'd also like to introduce the moderator of this session. It's Alina Konstantin, who's also a project officer from IAEA. So welcome, and the show is all yours.
Thank you very much, Fred, and hello everybody, and welcome to this event on AI for nuclear energy under the AI for Good Summit. We proposed this event earlier this year as a cooperation between International Atomic Energy Agency, IAEA, and the International Telecommunication Union, ITU. And now we are very pleased to see more than 1,000 registration for this event, which clearly shows interest and development in this area. AI can provide solutions in this era of digitalization and can pave the path forward to a sustainable future of the nuclear power industry. And today we have gathered to discuss the vision and path forward to nuclear 4.0 with the help of the AI. We have 90 minutes event today with 4 distinguished speakers from nuclear industry who will be sharing their thoughts and insights throughout the event. With dedicated short talks, a panel discussion, and the Q&A session, we are sure the event is going to be very engaging. Please keep sending us your question as well throughout the event. I will not allocate more time to introduction, but we want to thank the whole team from ITU, specifically Reinhard, Fred, Ida, Bastian, for their continued support, and from IEA, our Deputy Director General, Mr. Mikhail Chudakov, whom you will hear shortly, Mr. Dohi Han, the Director of Division of Nuclear Power, Mr. Stefano Monti, the Section Head of Nuclear Power Technology Development Section, Mr. Paul Vince, former Section Head of Nuclear Power Engineering Section, and Mr. Janos Eiler, Nuclear Engineer in Nuclear Power in Engineering Section. With that brief introduction and acknowledgement, I invite Mr. Jae-Sub Lee, the Director of the Telecommunication Standardization Bureau of ITU, to give his opening remarks. Mr. Lee, the floor is yours.
Thank you very much, Alina. Very good day, everyone. Welcome to today's episode, AI for Nuclear Energy, on the series of this AI for Good. Last week, we broadcast an episode on AI for atoms. which was curated by our sister organization, International Atomic Energy Agency, IAEA. This week, it's a great pleasure to welcome different set of our colleagues from the IAEA who curated today's program on AI and nuclear energy. As we may have a different audience from what we had last time, let me briefly introduce ITU's work on artificial intelligence and machine learning. ITU is the International Telecommunication Union, is a United Nations special agency for information and communication technologies. We are a global membership of 193 member states and over 900 companies, universities, and international regional organizations. ITU coordinates the global allocation of radio frequency spectrum and the satellite orbital positions. So we develop international standards that make the communication network run. And we support countries around the world in advancing their information and communication development. We also provide AI for good, like today, a publishing and collaboration platform. AI for Good is not just ITU's platform, but also your platform. Everyone who can contribute on how AI can help achieve the sustainable development goals is welcome to present on AI for Good. ITU does a lot of technical work on AI and machine learning. Much of this work has originated by the AI for Good platform. A significant part of the technical work takes place in groups we called focus groups. This is also open platforms, no need of this ITU membership. So let me briefly make some examples. A very exciting area of our work is in the focus group on AI for health, driven by ITU together with WHO. This group is developing a process to test the quality of AI for health solutions so that you can trust AI solutions. We have delivered a standard tool set to integrate machine learning into 5G networks and the future networks. We have a focus group studying environmental efficiency in view of the latest advances in frontiers such as AI machine learning. A focus group that operates together with the World Meteorological Organization and the United Nations Environment Program works on AI for natural disaster management. We have a focus group working to monitor and assess the behavioral performance of the AI drivers in control of automated vehicles. We just started AI for Road Safety Initiative, established in partnership with offices of the UN Secretary General's Special Envoy for Road Safety, as well as the UN Secretary General's Envoy for Technology. And finally, our most recent focus group, established just a few weeks ago, had the Food and Agriculture Organization of the United Nations as a partner, and we examine AI and Internet of Things for digital agriculture. So we are also running machine learning competitions. Our ITU Machine Learning in 5G Challenge is a competition which are running for the second time this year with hundreds of students and professionals from over 80 countries participating. We are also about to start a challenge on geospatial AI next year. Perhaps one of these services and instruments are of interest to you. So we look forward to continuing of this working together to ensure that AI is a positive force that helps us to achieve the sustainable development goals. So this is one of our case. I really wish you a successful event today. Thank you very much.
Thank you very much, Mr. Lee, for your opening remarks. And now, Gino, can I kindly ask you to play the video of our DDG for the opening remarks?
Ladies and gentlemen, distinguished speakers, dear colleagues, good afternoon from Vienna. It is my pleasure to speak to you at this Artificial Intelligence for Nuclear Energy webinar. Over the last several decades, digital technologies have had a massive impact on the workplace. Nuclear power facilities are no exception. Thanks to rapid advancement in computational resources and data analysis tools, the nuclear power industry is already benefiting from machine learning and deep learning techniques to streamline and optimize nuclear power plant operations and maintenance, including supporting the development of new advanced nuclear power technologies. But there still remains a huge untapped potential for artificial intelligence that can be used to plan and implement nuclear activities effectively and safely. Let us not forget that nuclear power generates about 10% of the world's electricity, which amounts to more than a quarter of all low-carbon electricity. In order to be competitive as well as integrated into the mix of modern energy systems, nuclear power plants, in addition to being safe, reliable and sustainable, also need to be economical and efficient. AI-based approaches can contribute in these areas. As we know, AI offers the capability of leveraging massive amounts of complex data in ways that were previously impossible to do by human or traditional techniques. This is why there is a great potential for the nuclear industry to capitalize on these technological advancements. The IAEA recently hosted a technical meeting on artificial intelligence for nuclear technology and applications and explored the main opportunities for AI to have a positive impact on the nuclear power industry. Automation, optimization, analytics, prediction and prognostics, and finally knowledge management were some of the themes and benefits that kept on coming up when we talk about AI in nuclear energy, and I would like to highlight them here today. As you know, operating a nuclear facility is a complex undertaking. With automation, AI can increase the reliability of tasks normally conducted by staff in high pressure and demanding situations, mitigating human factor errors and risk to personal safety. Anomaly detection, decision making and report analysis are some of the very tangible benefits we have from automation in NPPs today. Of course, understanding the benefits of automation leads us to optimization. AI can help us increase the efficiency and design of complex procedures and operations, such as outage scheduling, in-core fuel management, and fuel cycle parameters. AI methods can, for instance, be leveraged to expedite the characterization and validation of materials for new reactor generation designs, reducing the time and cost of necessary materials research. By using analytics to increase the quality of current models, AI methods can also help develop new quality assurance practices for manufactured components. This could be particularly useful for small and micro reactors. We can optimize the design of experiments to reduce cost and uncertainties and develop advanced dispatch and control methods for both energy and heat process applications, not to mention optimized strategies for how nuclear fits in hybrid energy systems. Ladies and gentlemen, AI has an important role to play in prediction and prognostics. Data science approaches can be leveraged to predict events, including failures, and the assessment of current asset conditions. NPP operators can use these tools to plan their maintenance and outage strategies, potentially reducing unexpected downtimes and minimizing periodic inspections. Finally, AI can enable the capture, codification, and retention of human expertise to support machine-led decisions. Knowledge management and knowledge transfer are key components for ensuring the success of highly technical industries like that of nuclear power. So as you see, when we talk about AI and nuclear energy, the use of artificial intelligence has the potential to make nuclear power plants more efficient to operate and maintain, and more flexible as part of the mixed grid. But these benefits don't come without a certain set of challenges. Confidence, measuring AI's overall performance and robustness, cybersecurity, which ensures the trustworthiness and the integrity of models, and data used for decision making, including regulatory concerns, which require an assessment of system vulnerability, must all be addressed. Here at the IAA, we are beginning to explore the added value of adopting AI technologies for the nuclear industry. This includes its associated challenges, regulations, and standardization procedures, all of which are required to ensure AI's success in our field. Ladies and gentlemen, it also comes to no surprise that machine learning and deep learning are being considered for fusion research. For example, at JET, the Joint European Torus, an operational magnetically confined plasma physics experiment, scientists have already trained their models using power and radiation data from 48 sensors connected to the jet reactor to predict disruption in a superhot plasma. This can result in plasma escaping confinement, jolting equipment, or ending the reaction. Scientists could use this process to better understand what ultimately leads to disruption and eventually run reactions where disruptions are less likely. Ladies and gentlemen, adopting innovative technologies and processes, including demonstrated successes from other industries, could quickly produce results and changes in our industry. Be it from digitalization or artificial intelligence, innovation could and should be found in all stages of the nuclear fuel cycle, in all nuclear operating facilities. That is why we are happy to be part of the AI for Good Summit here today. We are looking forward to hearing your thoughts on future developments and challenges for the deployment of AI technologies in nuclear energy. Thank you.
Thank you very much. And now we will proceed further and hear from our distinguished speakers and gain an insight on their AI-related projects and activities, moving then into the panel session and the Q&A session. Please send us your questions through the chat box. And now I will invite Mr. Boris Makevnin, who is the CEO of the private institution Chief Room of the State Corporation Rosatom, to speak about AI application in Rosatom, highlighting on the use of AI for MPP turbo generator anomaly detection. Boris, the floor is yours.
Yes, I'm here. Thank you very much, Alina. Gino, can you share my slides, please? Thank you very much. So, Fred, Chirayo, Alina, and the whole team, thank you very much for such a great opportunity to touch a surface of how the AI can bring the good for the people, and particularly through the application in the nuclear industry. That's quite an important topic for us. So can we go to the next slide, please? And for everybody on the line, good morning, good day, or good evening, depends on the time zone where you are. So Rosatom at a glance. I wouldn't go deeply into details about explaining what the Rosatom is, but just to give you a couple of numbers to keep in mind, and that would help you in the future. So the Rosatom right now operates in more than 50 countries. So it's quite an international, a global company where we have more than 300 legal entities under this umbrella of the Rosatom, and those legal entities are not only belongs to the nuclear plants, right? So we have the nuclear plants as well. You know, of course, this is our core product, but we have mining, we have R&D, we have machinery, we have manufacturing, we have healthcare, we have alternative energy sources. So it's kind of quite a diverse business which we are operating in, right? So can we go to the next slide, please? So since 2018, like 3 years in a row right now. We are operating, so within the Rosatom, we have the digital strategy, which actually, firms all together how we use the different tools, techniques, and processes of the digitalization to improve the both internal operations and more, going, beyond just the nuclear industry. How do we improve the way we interact with our clients, with our users, and with our partners? And if you'll think about, that's a kind of the details, the high-level analysis of the portfolio of all the projects and initiatives which are right now, goes into this this digital strategy. And if you think about AI, it takes 22% of all the, and right now there's like slightly above 200 initiatives, which is, and we count only the big ones. So it takes like 22% of the entire portfolio. And especially the AI strategy takes its fair part in our overall digital strategy of the Rosatom. And again, as I said, we have invented one in 2018, and we kind of gradually, I wouldn't say upgrade, but gradually, that's probably, let's use the word upgrade or fine tune it on the annual basis, right? So what we see, we don't have the statistics on the screen right now, but we see is that over these 3 years, since the 2018, the interest, importance in the way how the business and our employees and our clients see A, importance, and B, what is the most important results of the AI on a daily basis is actually growing up. So this year it's 22%. 2 years ago it was slower number, means like I don't remember exactly, but it was like 10 or 12%. So it's growing, right? So the business employees and the partners sees the results which AI is actually brings to the different group of businesses which I highlighted before. Can we go to the next slide, please? Well, if we'll speak about AI, because AI is kind of it's a kind of a cloud, right? So it's a big number of techniques and the ways how do you apply for different things. So if you'll think on the practical side, there are like 3 most popular segments of the groups which are demanded within the Rosatom group of companies. So predictive analytics, and when we say predictive analytics, it's not just the predictive maintenance, but it's also some prediction on the different behaviors on the client, of the business processes, the way how the processes would be going in a different way. So it's not just the predictive maintenance. It's like the big meaning of the predictive analytics. The natural language processing, where we have both speech recognition, text recognition, where we actually work on the different, where we see how we can embed or enrich our existing classic services with the tools which can help it, be more efficient. For example, we use right now the neural nets and the machine learning application for, working with our technical documentation while we're preparing and analyzing the requirements for the construction. Right? I wouldn't go very much into details, but just to give you a little bit of what could be the text recognition application within the nuclear industry, and the computer vision, where yes, we use a picture of this self-driving car or kind of the assistant which helps the car to go on the way. It's not actually the case of the Rosatom, so we use it as the most common picture. But for the computer vision, we use it right now as the video analytics on the plants and on the different facilities, and we use it for analysis and the quality of the produced equipment. So, for example, the fourth one group and the first 3 one is actually we already have the operationalized examples, right? So all this, it's not just the MVPs or pilots. Those where we have the projects which were already embedded into our daily operations. The fourth one is actually we're quite intensively invest in the R&D piece, and this is where we are right now interested, particularly in the neuromorphic machine learning and artificial intelligence and the quantum artificial intelligence. So those are kind of two big R&D pipelines for us, where we do believe the result would be also quite heavily applicable within the nuclear industry. So can we go to the next slide, please? So now, as I say, like we have the three main groups, and among those three groups is like the predictive maintenance, the predictive analytics is a king, right? So if you say like those three groups is 100%, so the predictive analytics is actually takes roughly like 60% probably, right? So it's a huge. And here is giving you quite a practical example with kind of like as I said at the beginning, we're really like touching the surface, right? The surface. So we don't go very deep into details with all the mechanics in the code, but let's take an example of one of our projects with turbine generator at the nuclear power plant, right? So can we go to the next slide? Yeah. So why size of a price? Why do we care, right? So why we're speaking about predictive maintenance applicable to this case? Is we'll give you a kind of an average numbers, right? So it's because all the turbine generators are different, depends on the plants, etc. We also, but in average, if you have the emergency stop of a turbo generator, and I would use the turbo generator instead of turbine generator, it costs you like €1 million a day. It's kind of the lost profit. And when you say the lost profit means like you cannot produce the energy, but we cannot also calculate, the value which this energy can give to the consumers of this energy, right? So it's €1 million. It's on our side. It's probably higher on the side of the consumers, which is hard to calculate, and that's only part of the loss, right? So size of the price or size of the issue is like the loss, and comparing to the loss is a minor one, but still yet to be calculated. It's actually the cost of the repair in case of the emergency stop. Because if you have an emergency stop, usually it means like something goes significantly wrong. You have to reshape it. It takes more than 1 day to fix it. In some of the cases, I don't want to give you statistics, how does it split, how many days it takes, but it's usually you have an emergency stop, it usually takes longer than a day to fix. If you use the predictive management and predict the way how your turbine generator is actually going on the wrong way, you can do a planned stop, because usually you have the planned stops on the queue, but you can anticipate and you can make it the planned stop earlier, use the very kind of short and fixed time to fix the stuff, and then goes further smoothly. Can we go to the next slide, please? So if you'll think about turbine generator, so usually it's kind of the 500-600 sensors, which are in a generated constant, in most of the cases constant data flow, which we're applying the machine learning based algorithms to anomaly detection. You can actually predict the way when this can you go to on the next slide, please? When you go from the when you go on the actually the accident way threshold, it feels it's kind of a funny way. So find the difference between those two pictures, like on the left and on the right. But on the left, you have an accident, which is, you know, this pointer stuff, where the accident is happening, right? And if you go back and apply the machine learning algorithms, which on the way identify the defect, is actually you eliminate this time A between defect and the accident. You shorter the time after the accident to fix the turbo generator, and you actually saves, you know, all this money, which then you would anyways invest in fixing the problem. So like the early defects detection can reduce the repair costs significantly. Can we go on the next one? So that's you know, we've got, you know, a lot of you know, learnings, and some of them I've tried to put here on the slide. This is comparing to the cost of the maintenance and the cost of the repair, the investment into this quite a simple machine learning algorithm is you know, the cost of the model comparing to the cost of the repair. You know, the cost of the model is actually kind of going to the zero, right? So it's incomparably small. It's kind of almost the rounding mistake, right? So it's a definitely way to invest, at least for us, the way we see it right now, because we are kind of, you know, finding up a couple of the pilot projects to identify the most convenient circumstances for us to introduce them, those algorithms into the overall operating model. But you know, the cost of the model comparing to the cost of this machine stop is actually, you know, rounding mistake. So that's from the economy standpoint, that's a very efficient way to invest resources and efforts. B, for us, what we found is that the way how to use structure this data around, you know, it's quite an important in order to have this use case scalable among the other turbine sets, among the other power plants. It's quite important the way how you structure the data. And that goes because there was one of the questions on the line. So where we can get the data sets, how do we manage the data sets, you know, how do we share the data? So for us, the clean data and some clear standards and the way how do you describe the data sets and how do you describe the rules, how do you store, collect, and then provide the data to the developers and to the data scientists is kind of an essential prerequisite for a sufficient machine learning algorithm deployment, and B, the way how then you can scale it among the other solutions. So it's quite, that's it probably on our side. Again, coming back, we have, that's probably one the simplest case of the AI application on the perimeter of our company. We have plenty of the others, so you know, I hope there will be more the webinars and forums like that where we can go deeper and more into details, because what we truly believe in, AI significantly improves the daily operations. Of course, there's a lot of kind of circumstances which have to be put in place in order to make it efficient and effective. But again, like, AI is all for good, and we kind of live with this in mind for like already quite a few years in a row. Thank you very much, and for all the others, have a great session.
Thank you very much, Boris. As mentioned, we will take the questions in the Q&A session. So please keep posting in the chat box. And now I will give the floor to Mr. Aurelian Schwartz, who is the CEO and co-founder of Metroscope, a fast-growing tech company leveraging AI for industrial monitoring and diagnosis. And he will speak about how to use digital twins for nuclear plant monitoring. Aurelian, the floor is yours.
Thank you very much, Alina. Can you see my screen well? I hope so.
Yes.
Perfect. Then I will be speaking about how we use digital twin for nuclear plant monitoring. So as you were saying, Alina, I'm CEO of Metroscope. Metroscope is a software startup founded in Paris in 2018. And I am myself here in Paris. So it's almost the evening here. And we are already equipping more than 60 power plants, including 58 nuclear power plants around the world already with our monitoring AI technology. So what I will do during that session is I will present our technology. I will present a very concrete use case so that you can understand how we build digital twin and how we use them. We leverage that technology to eventually provide monitoring and diagnostics value to our customers. Starting with EDF in France, Metroscope is a subsidiary of EDF. EDF is the first nuclear operator in France. And Metroscope currently is monitoring all the nuclear plants in France. It accounts for 56 PWR just on the French soil. So for that presentation, I thought of going for a use case. So I will introduce a unit. Let's call it Unit X. It's a PWR. It exists. It's in France. And I will use that Unit X as my let's say, as my test case, so that I will show you what we can diagnose directly on that nuclear plant. So it's a nuclear plant in France, south of France. Initial operation started in 1980. The overall power generation of Unit X is 900 megawatts. It's been manufactured by Framatome. And so the goal of the monitoring is to try to observe all the measurements that will come from Unit X and test whether it functions correctly or not. And then we will try to understand what are the root causes of any problem, faults that can happen on the process and would have an impact on the power generation of that unit. So I will start with the end and showing you exactly what I mean by monitoring and what are the outputs of our digital twin before going back to how we build that and what is the technology. First, the performance. So I was telling you, Unit X has been designed for 900 megawatts, but let's go on the 9th of January 2019. And you see on the right here, some results from Metroscope, from the software, directly calculated by the digital twin, where you see this green curve and this blue curve. The green curve stands for how much shall the plant generate right now, which is 963.5 megawatts. And the blue one is how much is it performing technically in reality, which is 959.9 megawatts. So here we see, first thing, that we are losing 3.6 megawatts due to internal losses. So this is the first statement that we bring, and that is already really important because this is what we call a symptom. We detect that we have a difference between an expected value for the power generation of that unit and the real value coming out of the alternator and actually generated for the grid. So then the question is quite naturally, okay, we detect that there is a deviation between those two measurements, but then the question is, what has happened? Can we understand the underlying cause and then get to fix it? Because eventually we want to go back to full power and then we want to fix it. And this is the second part of my use case, which is on the very same day, something happened. We have diagnosed automatically through our algorithms, through our AI, 3 different problems. I will just show you one here. This problem on the 9th of January 2019 on that specific plant is what we call a tube rupture in a feed water reheater. So a reheater is a heat exchanger that is a 2-phase flow heat exchanger, and you have a lot of tubes within. And if you have some tubes that are broken, then it leaks. And eventually you want to fix that. So you need to have a maintenance operation to go and fix it. So the sooner you detect it, the better, obviously, for your maintenance operation. Here you can see that Metroscope, the software, the AI that is behind, has detected the problem on December 23 with a magnitude of 3 kilograms per second of leak. It has been fixed by the maintenance team more than 2 months later at a magnitude of 15 kilograms per second. So it's very easy here to understand the value of the digital twin that will bring us that diagnostic. Eventually you will fix sooner and you get a better knowledge In introduction, the speaker told about the importance of AI for knowledge management. Here you get a better knowledge of what is happening on your plant, and so it eases all the decision making. So then the question behind that is, how did we do that? Because there is obviously no instrumentation in that reheater. There is no way for directly understanding what is happening. So you need to go there to be able to leverage a lot of technology actually to get to that result. So I will try to explain a little bit about that. First, what is a digital twin? I've been saying that we use digital twin. I took the definition from the Gartner. I find it quite accurate. So digital twin, it's a digital representation of a real world entity or system. And it is encapsulated in a software that mirrors this very object or process so that then you can make some decision making, which is eventually the goal of any artificial intelligence, which is easing a complex decision making based on data and based here on the digital twin. Back to Metroscope, what does it mean for us at Metroscope? This is right now a model of that Unit X nuclear power plant in south of France. You can see on the right, you have a complex scheme, which actually is simplified here, where you have the steam generator, the turbine, you have the different components. In reality, you have 135 components, and they together are what we call the secondary system in charge of conveying the thermal power coming from the primary circuit all the way to the alternator in order to provide electricity to the grid. On that specific unit, to build the model, we had to build 12,000 physical equations in that model, relying on 95 measurements and 5 years of data history. So why do we build that model? First, to have a reference, to know how the plant should be working if everything was perfectly fine. So this is the first model, but it's not enough to go to the root cause diagnostics that I've been speaking about and that I introduced in my previous slides. You need to embed in that model the problems that can happen. And this is the next step. First, we build the model, and then we build the fault library. So you have plenty of different failure modes, problems, faults that can happen to different components. And you want to model them as well so that your digital twin is able to tell you when everything is working well, but also when you have problems. You want to be able to simulate the consequence of anything happening on your site in order to do the detection. So in a standard nuclear power plant, we have up to 80 ways of detecting different failures on the plant. Here you have a few examples. It can go from problem on valve to, I was introducing earlier, tube leakage or problem with your condenser that can have some hair intakes, etc. I'm not going into details here, but the idea is that you don't need just a model, you need a model and you need the faults that can happen. This is where you really store your expertise. Third step, it's not yet enough to actually make the decision making. You need an algorithm that will do the decision making. So what I just introduced, that was the digital twin. This is the orange brick that you see here. It gives us the expected behavior of the plant, and it gives us the faulty behavior of the plant. But then what do you want to do to be able to provide a diagnostic? You need to be able to take into account in real time all the measurements that come from the sensor of the plant, all the output of the digital twin on the other side, giving you the expected behavior and the faulty behavior. And eventually from that, from those two information, you want to tell the operator who is in charge of running and fixing the plant what is happening. So you are eventually trying to answer that equation here, which is the diagnostics are the probability of the problem knowing the symptoms, which are essentially what you have when you go to the medicine. If you go to the medical doctor, you will have some symptoms, you will have a headache whatsoever, and you need to go back to what led you to have a headache. That's exactly the same here. We build symptoms from our digital, and eventually we will build the diagnostics. And if I'm going back to Unit X, and you will see that is quite obvious here. Here you will see Unit X over 2 years of history. Over those 2 years, that digital twin technology enables us to find all the different faults that happened. So here you can see 7 faults that have been automatically diagnosed over 2 years of history for Unit X. And something quite important as well is that it's very reliable, because in 90% of the time, the operator has confirmed the detection that was suggested by the algorithm. So in a nutshell, and that's where I wanted to go with all that, building a digital twin is a mature technology now. We can really use it to do the monitoring, and it can bring a lot of value by automating a very complex decision-making on the plant, and it's already used, it's already equipping a lot of nuclear plants, but not only, because you can also adapt the digital twin to other assets. So when we speak about nuclear plants, the value is obviously to have more power generation, to have a better maintenance decision on the plant, but also to better share the knowledge within the organization. And if we think about other assets like conventional power plants, like gas generation, for instance, it will also have a very strong impact on the environment, because it will lower the CO2 emission of the assets. So overall, this is, I think, a technology that is very well in the team of that webinar, which is AI for Good. And I hope that that demonstration was convincing, and you really understand how we can impact the future of nuclear power and monitoring by leveraging the digital twin. Thanks a lot for your attention all.
Thank you very much, Aurélien, for this very, very interesting presentation. Please put the question in the chat. I already see that discussions are going there. We will take questions soon. And now I will invite Ms. Heather Feldman, who is the Director of Innovation in the Nuclear Sector at the Electric Power Research Institute, EPRI, and she is leading EPRI's initiative on artificial intelligence. She will speak today about AI for operation and maintenance for nuclear reactors. Heather, the floor is yours. We do not hear you, Heather.
My apologies. Well, hi, everybody. I'm Heather Feldman, and it's great to be with you all this morning. I'm joining in from North Carolina here in the United States, and looking forward to a great conversation about the application of artificial intelligence in the nuclear power industry. What I'm going to speak about is really focused on using AI for operations and maintenance at a nuclear power plant. And EPRI has been working in this area for many, many years. And then recently we've incorporated artificial intelligence as a tool in our toolbox as we continue to improve the efficiency of operations and maintenance at a nuclear power plant. A few years ago, we did start an initiative on artificial intelligence, and our website is ai.epri.com if you're interested in learning more and seeing what we're doing in this space. EPRI is a non-for-profit research and development organization that's focused on the end-to-end power system. Our mission is to advance safe, reliable, and clean energy for society through global collaboration, science and technology innovation, and applied research. So with that as some background information, let's jump in and talk about AI in nuclear power plant applications. So here's a visual of somebody that works at a nuclear power plant. So imagine with me, you work at a nuclear power plant and you've worked there for a long period of time, and you can walk through the plant and listen for a pump that doesn't sound right. You might look at a pipe and see that it's vibrating, but it's not vibrating the way it normally does. And as you're walking through the plant, you're making these observations because you have a significant amount of experience and you're familiar with operation and maintenance of the plant. Now let's take that same viewpoint and see what artificial intelligence could do for us. Let's see what automation could do for us. So nuclear power plants today are starting to incorporate a wireless backbone into the facilities, which would enable wireless sensors to be added to various pieces of equipment, various pipes, and so on. There's electronic work packages that are being deployed such that workers in the field are walking through the plant with an iPad and understanding the work scope via that digital technology. There are efforts underway to monitor chemistry, to automate chemistry. There's efforts underway to look at radiation monitoring throughout the plant, to look at how to monitor a pipe, and so on. So there's many, many opportunities to automate different processes at a nuclear power plant. And AI is one tool that can be used to automate those processes. So at EPRI, as we began to look into broader application of artificial intelligence, we started to think about this in the 4 quadrants that are shown here. First one being around insights. How can artificial intelligence be used to gain insights from information that we have available today? The second area is optimization. How can we use artificial intelligence to better optimize a process that we have in place today? The third area is around prognostics. How can we use artificial intelligence to better predict what's happening around degradation of a pipe, as an example? And then the last area is automation. How can we use artificial intelligence to automate different tasks? At the bottom of this slide, what I'm showing here are the EPRI 10 data sets across the electric power industry. So this goes beyond the nuclear industry, but these are the EPRI 10, the 10 data sets that EPRI is pulling together such that we will have global data sets in these areas that can be used to address and solve problems and produce opportunities using artificial intelligence. So what I'm going to do now is walk through 4 use cases where we're doing some work, again, focused around maintenance and operations. So the first use case that I wanted to talk about was the development of basically a dictionary, a nuclear power dictionary, such that it can be used for natural language processing applications. So we wanted to start small. We wanted to start with a use case. So we took a look at using artificial intelligence, using natural language processing to better understand groundwater contamination and using available information, available reports that are out there. So we used information from EPRI, we used publicly available information, we used some information from INPO as well. And what we learned through this process is that the natural language processing dictionaries that are out there today aren't uniquely tuned for the nuclear power industry. For example, if the word plant is used, the definition is, something green that grows out of the ground, whereas when we're using plant in the context of a nuclear power plant, it obviously means something very, very different. So we are in the process of collaborating with organizations from around the world to build out a nuclear power dictionary that can be used with natural language process applications. It's just a tool that can be added into applications as developers are out there developing different applications. So we're in the process of building that out. Available information will come out in the middle of 2022. And that first example builds on, is the basis for this second example. So we're working on a project to automate the review of corrective actions. So in a nuclear power plant, there might be on the order of, say, 50 corrective action reports that are written each day. And each of those reports is reviewed by a person, reviewed by a worker to decide what the next steps are. So we are in the process of using natural language processing to screen those corrective action reports. We have data from over 13 nuclear reactors, 3 years worth of data. And we're building out a tool to basically automate the review of those corrective action reports. We did form an industry working group, most recently met back in September, and we're just working our way through developing this technology. This technology will leverage the nuclear power dictionary that I just mentioned. The third application that I wanted to talk about takes us over into the monitoring of flow accelerated corrosion throughout the plant. EPRI has a tool called CheckWorks. It's a software package that's used to predict flow accelerated corrosion in different components. What we did with this particular project is we took about 27,000 inspection data sets from 48 different units and used artificial intelligence to predict what the degradation would be in these particular pipes and components. And what we were able to see is that the predictions were actually better than the techniques that we're using today. This project is still in its early phase, so we will continue to develop the artificial intelligence techniques for the prediction of flow accelerated corrosion. And then the final example that I wanted to talk about is a machine vision model. This one is focused on automatically detecting damage in concrete. So as you can imagine, doing an inspection of concrete containment, you have people that are up on scaffolding, they're using visual techniques and other techniques to really get a feel for what's happening in the concrete. An alternative to that would be to use drones to collect image analysis data and then use artificial intelligence to basically process that image data, that video data, to identify when there's corrosion, when there's cracking, when there might be some spalling. So at this point in time, we have a tool that's available for field testing. We need to get out there in the field and actually test things out and see how well it's doing. In addition to that, we are collecting data and anonymizing that data and are going to be able to share that data set out sometime next year. So we're really looking forward to that as well. So I wanted to this morning just take us on a journey through a nuclear power plant and talk about a few use cases where we're taking artificial intelligence as a tool in the toolbox and applying it to how we maintain and operate plants today. So Alina, I'll turn things back over to you.
Thank you very much, Heather. Thank you for this very interesting presentation. Now I will give the floor to Mr. Dawei B, who is the Director of the Department of Digitalization Engineering at the Shanghai Nuclear Engineering Research and Design Institute, NERDI, and has been working on the cross-cutting field for more than 10 years. And he will speak today about developing international standards on AI for nuclear energy. Dawei, the floor is yours. Dawei, we do not hear you yet. We cannot hear you, and
yeah, you should be able to hear me right now.
Now we hear you, but we don't see the presentation anymore.
Yeah, sure. So can you see my presentation right now?
Yes, perfect. Thank you.
Okay. Sorry. I forgot to unmute myself. Alina, thank you very much for the introduction, and good evening from China, and good morning, good day, and good evenings to the audiences online. It's really a privilege to be invited here to share some of my work on developing international standards on AI for nuclear energy. I'm from Shanghai, so I work with SNERDI, which is a leading nuclear energy research and design institute. We developed, designed the first nuclear power plant in the mainland of China, and currently we are working on one of the very important national science and technology major project on advanced PWRs. And with that project, we are working on a lot of cutting-edge technologies, including AI. Well, honestly, AI is a buzzword right now. Everybody are talking about AI. Is several years ago, AI beat world champions at the game of Go. And right now, AI can interpret your mind and change your thought into handwritings. And AI is also not missing in our combat against COVID-19. AI has been used to read CT scans for the virus detection. And there is no exception for nuclear energy. As we can see from the DDG's opening remarks and from the presentations of our co-speakers, AI is everywhere for nuclear energy. I don't want to repeat that. But what I want to say, just like every coin has two sides, there's also an inconvenient truth about AI for nuclear energy. The truth is AI seems to be elusive for nuclear energy. Well, we are talking about AI tonight for me. Well, people are talking about different things. Boris are talking about anomaly detection. And the Orlean are talking about digital twins. And Heather talking about, for example, NLPs for automating cap data processing. Well, they are all AI. Well, essentially, what's AI? Different people may have a different interpretation of AI. It's very important that we have a common understanding of AI. The second question is, what can be done or what cannot be done by AI? Some people are optimistic. They think AI is almighty. They can do everything. But some people are skeptical. They believe AI is a black box. They doubt it. So it's very important to know what can be done and what cannot be done with AI for nuclear. And finally, and very importantly, every people here, they listen to the presentations. They may want to use the use cases, the methods presented here in the webinar to their own work. They will find it far from being easy to implement that. How can we efficiently and effectively deploy AI? This is a very big challenge. So my humble perspective is that standardization is key to resolve this similar paradox. With standardization, we can have common terminologies. We can understand the state of the art, and we can be clear about the stage of maturities. Personally, I'm working within IEC on this kind of work of standardization. As many of you know or may not know, IEC is like ITU that develops standards concerning electrical technologies. It have a dedicated subcommittee 45A that works on electronic and electrical functions for nuclear energy generations, and in particular, its scope covers artificial intelligence. Last year, in the plenary meeting of subcommittee 45A, I met an initiative at that meeting. I made a presentation titled From Instrumentation to Intelligence. I proposed and advocated that 45A started work on standard development on AI for nuclear energy. I'm glad that this presentation is well received, and 45A decided we start a new project to develop a TAR on AI applications for nuclear installations. And I'm privileged to be appointed as a leader for this project. Right now, we have many experts from 7 major nuclear energy countries. Well, with this project, we want to lay the foundation for the future work of IEC 45A. Maybe we will look at the next 20th plan for our standard development efforts. With the current work, we will try to answer the 3 questions we have raised in previous slides. First, what's AI? Well, in this regard, we don't want to reinvent the wheel. Essentially, we will follow the terminologies and concepts set in IEC, ISO, GTC 1, subcommittee 42. This is a dedicated subcommittee on artificial intelligence, which was created in 2017. It has a lot of good standards for people to have a common ground to understand AI and exchange ideas about AI. The second questions about, of course, we will also refer to other SDO's documents. For example, ITU. ITU also have some standards on AI applications. We will refer to their work when necessary. We will try to answer the second question too. Well, essentially, we will look at what can be done by AI for nuclear energy. There's a lot of examples in today's webinars, but for me, we'll look at these questions from 2 perspectives. First, we'll try to explain AI in more readable text to people who don't know too much about AI, but who is enthusiastic about using AI for nuclear energy. The second perspective is that we want to capture the proven or potential AI applications for nuclear energy. Today's webinar is a very good input for us too. And it's interesting to note that actually AI is it's not new for the nuclear energy industry. It has been actually started for several decades, and much knowledge has been accumulated internationally. This is a good basis for our work at 45A. And finally, and even more importantly and practically important, is we will work on how to enable wide adoption of AIs for specific applications. The answer is to develop specific standards. For example, Boris talked about the anomaly detection. We plan to have a standard dedicated to the topic about anomaly detection for a variety of applications, but anomaly detection itself is a very important topic. We plan to have a standard on this. Of course, we will also, for example, have a standard on digital twins applications as well. Well, this is our preliminary thoughts about these topics. So our philosophy can be seen easier in these slides. Essentially, we think the standards for AI applications in nuclear energy may it be composed of 3 tiers: the fundamental standards, horizontal standards, and vertical standards. Fundamental standards, well, essentially will refer to AI standards from GTC 1 Subcommittee 2 series. Horizontal standards is very important. It will cover a lot of topics that's of relevance to our applications in nuclear industry and important to varieties of applications. For example, we'll look at the risk assessment of the AI applications. We'll also look at the data quality management for AI for nuclear energy. We expect to have the most of our standards fall into the categories of vertical standards. We will cover the full life cycle of the nuclear energy life cycle. We'll have a standard different important topics. Well, this is a very, honestly, this is a huge ambition, and we expect that it will take a very, very long time, but we will start with small. We will try to finish our current project by the year after the next year. And I would also love to take this opportunity to invite comments and contributions from the audience online. Yeah, this is a very, well, you know, the topic, well, is very big. We can't achieve our ambitious goal without support from experts from the world. We hope together we can reshape the landscape of AI for nuclear energy. Thank you very much for your attention.
Thank you very much, Dawei. Very interesting presentation, and thank all the speakers for their insight. And I guess now the whole audience have very, very good insight into the range of possibilities and potential of AI for nuclear energy. And now we will move to the panel session to discuss on some common aspects, and just a short note that due to an unexpected situation, Boris needed to leave, and he will be replaced for the rest of the event by Mr. Dimitri Stitnik, the head of AI department in GIFRUM. So now, yeah, I see you are still sharing the screen that way. Maybe you can. Yeah, good. Thank you. So I will start with a first question addressed to all of you. What about the challenges related to change management? Some organizations may be reluctant to this, to adopting AI for nuclear.
So may I say first?
Yes, please.
Yeah, so from my experience, for the change management, it's very important that the top executives will support the adoption of new technologies. Without support from the very, very top management, it's not possible, or it will be very challenging. Well, that's I don't have this comment. Thank you.
Thank you, Dawei.
I can maybe bring you. Go ahead, Hester, if you want.
Okay, sure. I was going to agree. I was going to say one of my comments is, you know, good change management does start from the top of the organization. So it really needs to be supported from senior level executives, if not the CEO, for it to be successful. I was going to build off of that and say, as you're introducing new technologies such as artificial intelligence, expertise is really important. In the electric power industry, we have subject matter experts, for example, on a nuclear power plant that don't know artificial intelligence or don't have that data science expertise. And then we also have data scientists that have the data science expertise, but don't understand the electric power industry. So, you know, change management as you're rolling out a new technology, creating training opportunities and creating ways that the electric power experts can build out their artificial intelligence skills is really important, but also pulling in the AI community so that they're learning about the electric power industry is really important as well. And I'll pause there because I know my colleagues on this panel have other comments as well.
Well, I can pick a slightly different angle also about AI and change management, which is the tool itself. When you bring a tool to new people, first you need to win the trust. Winning the trust means that your result must be good and you need to display expertise, like you just say, Ether. But the other aspect to that is also that you actually need to care about the design of the tool and take into account the user experience, the user journey when you build the tool to make it easy to be adopted, because tools in the industry are often very complex, and that is often something that people will tell us, which is we don't want another tool because it's so hard to master every one of them. So AI makes it easier to have tools that are very intuitive, and you need to work both on the design part and have good results and have the management going for you as well. And so it's a combination of all that that will make that eventually people will accept it.
Thank you. I will move to another question that, we can detail a lot on this, I'm sure, but maybe you have a quick perspective. How to scale AI projects efficiently and fast? And maybe we can start with Heather.
Yeah, sure. So I mentioned several different use cases that we're working on here at EPRI, and really scaling is all about starting small, starting out with a use case, starting out with a pilot where you can really test out and experience the technology. You've got to get people on board as you go from use cases to an enterprise-wide scale. And I mentioned it earlier, but expertise is really important as well as you're going from use cases up to enterprise-wide expertise. It's something that needs to be done systematically. It's something that needs to be done with a plan. It's something that needs to be done with buy-in throughout the organization.
Thank you. Anyone else in the panel that would like to pick on this? If not, I have another question related to cybersecurity. So what about the accessibility of data? Because there are definitely challenges related to cybersecurity.
Oh, well, may I have some comment on this? So, this is a good question. Cybersecurity has been a limiting factors on the application of AI is because AI, everybody knows the current breakthrough in artificial intelligence is driven by, in part, the availability of a large amount of data. As Hesse have mentioned in her presentation, for their they have gathered a lot of data from the many inspections. So this from this we can see the importance of data. But of course, for nuclear applications, if we want to get the data, especially online from a lot of operating nuclear power plants, people will be very careful about the cybersecurity. So, maybe this can be resolved from two different perspectives. One is about the technology itself. Right now there are some advanced calculation methods called federated machine learning. This is essentially a distributed learning algorithms. The data will remain in the premise of the nuclear power plant. The data will not flow out of their power plant. This is one perspective. Another perspective is, it's dependent on your application scenarios. In most of the times, the utility owners will invite some vendors, AI vendors, to help them develop AI algorithms. In these cases, they don't, well, the data is within their own premise. So I'm optimistic about this. Well, thank you.
Thank you, Dawei. Thank you very much. Another question is related: how mature is the nuclear industry on AI compared to other industries? Maybe Dimitri can pick up on that. Oh, of course, each of you in the panel can also.
I think that,
yeah.
Can you hear me? I think that our industry is quite mature for using different AI algorithms, but I want to add something to my previous colleague, and we have to separate different types of tasks. For example, some critical tasks when we are working with critical data connected with reactor process and something like that, and some data, for example, like nuclear dictionary, for example, for some auto applications that is not so critical. And of course, it's more easier to develop some applications for not critical data, because we are working with different data sets, and when we don't have serious cybersecurity limitations, it's more easier to do such things.
Thank you,
just to
Dimitri.
add from my side, other than maturity, if you make this question more interesting for the speakers, are the regulators ready to license such new technologies? We might be mature, but are our regulators ready to license such new technologies? If you can add this also, it would be great.
I can speak a little bit if you about the other industries, because at Metroscope we don't only work on nuclear, but we also work with gas plants. We work also with cooling system on data centers. So we do the digital twin for different industry. And something that we've seen is that the nuclear industry is very advanced. Because everybody knows how to export the data, everybody is storing the data, everybody is looking at the data, everybody is already doing data analytics. There is not one single nuclear customer of Metroscope who doesn't have a monitoring and diagnostic center, who doesn't have an intern working on the data and trying AI today. So you have a lot of person trying to, and I can tell you that this is a huge step forward compared to what we see in other industry, where they just don't know how to export the data. They barely know how to use it in external tools. And there's another big shift that is empowering everybody, and that also apply to the nuclear, which is the shift to the cloud. That is also happening even in nuclear. We tend to think that in nuclear we will not go in the cloud. That might be true on certain data, but I can tell you that our experience is that the nuclear people, they have a lot of experts to go in the cloud and to make the cybersecurity reliable even in the cloud. Eventually, I do think that the cloud will be safer than on-premise solution, but there's a journey to go there. And every time we speak to nuclear customer, we see that IT people are very advanced, very educated to cloud. And we also see that data analytics people are also very advanced, and they can do a lot of things with their own data already. So my understanding is that when we monitor nuclear plants, and then when we monitor, let's say, for instance, a data center cooling system, there's a world. There's like 5 to 10 years difference between those two. So I do think that nuclear is actually pretty advanced.
Thank you, Aurelian. I see a lot of questions in the chat. I'm afraid we were not able to address all of them. But one for Dawei. You mentioned ITU is also developing AI standards. What is your suggestion to strengthen IEA, ITU, and IEC collaboration on AI for nuclear standard development effort?
Elena, thank you for the question. Very interesting question. Yeah. Well, as I have explained in my slides, international collaboration is very important to enable wide adoption of AI for nuclear energy. We don't want to reinvent the wheel, so we can use the current result from, for example, ITU. As one of my slides shows, ITU is developing some international standards, for example, for the image recognition. These kinds of applications can be referred in our industry. So I believe in the future we can have a close collaboration in this area. I believe this kinds of collaboration will benefit the whole industry. That's all. Thank you.
Thank you very much, Dawei. I have a question for Heather. What training is available on AI?
That's a really good question. So when we started working in artificial intelligence in a really focused way a few years back, we looked around to see what type of training was available out there. And we did pull some information together. We also identified a gap in that the training was tended to be focused on artificial intelligence experts or driving towards somebody becoming an expert at the end of this class. And the gap is really in helping electric power industry experts learn more about artificial intelligence so they can work better with people with those types of expertise. So we've developed a few courses that are out and available on our learning management system and our website that are really geared towards the electric power industry. We've got a class that's focused at the manager level, and then another class that's focused more on the technical level. So I'd say, there's great training that's available out there if you really want to dive deep and become an expert in artificial intelligence. And then EPRI's developed a few classes that are geared towards the electric power industry.
Thank you very much, Heather. I think we have time for one more question. If you can detail a bit about the using of AI for knowledge management and knowledge transfer, because definitely this is a critical area for the nuclear field, and how AI can support this.
Yeah, I can talk about one example in this area, and it goes towards steam generator tube inspections and an application that we worked on starting back in the 1990s. But going in and doing a steam generator inspection uses a technique called eddy current, and it requires deep expertise to analyze that data and understand whether or not there's some sort of degradation in the steam generator tube. And so what this particular application did was used artificial intelligence to automate the analysis of that data to determine whether or not a defect is there. This was years, almost decades in the making, to where the experts would analyze the data in parallel with the artificial intelligence tool until we built up a confidence in that artificial intelligence tool such that that auto analysis is used today. So that's one example of how artificial intelligence can be used to transfer expertise over a period of time with the right checks and balance in place, just to make sure that we're very comfortable and confident in the artificial intelligence application. And in that particular example, it's been accepted by the US Regulatory Commission.
Thank you very much.
Aurelian, yes. If I can just add to that example, another experiment that we had with Metroscope, we see that AI brings such an added value statement eventually that it's really easy to share. And one of the consequences that breaks the silos within the organization. Eventually, everybody agrees on the same source of information, and that creates trust within the organization, and that shares the knowledge within the organization, and that's very strong. Something that we've seen is when we gave the software to our users that were operator on site, we expected to have as many users as we have operators on site, And eventually, we ended up having 5 times more users because everybody from the corporate, they also wanted to have the tool because it was so easy to get the information. And so this is one good example of how it breaks the silos and how it just shares the knowledge within the organization and makes everybody agree. And then you don't need like 12 meetings to make sure that the boss understands what is the health of the plant right now, because you have like so many layers to get there. Everybody has the same tool. Everybody just sees the same information. That makes the life of everyone easy.
Thank you very much. I'm afraid that now we approach the end of this event. I'm truly amazed by the quality of the presentation and all the information provided here. It was very, very informative, and I hope all the audience here enjoyed this webinar. I was truly honored to moderate this, and I thank you all. But I want to mention and special thank my dear colleague Chirayu Batra, who was truly at the heart of this event. Without him, this event would not have been possible. So thank you very much to all of you, and special thanks to Chirayu. Chirayu, if you want to add some final words, please.
Thank you, Alina. Thank you, all the speakers. I think this was truly an insightful session for me, and I'm sure that everybody learned as I did. So for me, it was a big learning experience, and I'm sure this is also start of several activities that hopefully IEA will initiate, and I hope to see collaboration not only from the speakers, but also from the participants in our future activities. With this, I would like to hand over to Fred to make some closing remarks from ITU, and thank you everyone for attending this session with us. Thank you very much.
Yes, thank you, Chirayu, and for all your work organizing this session, and your colleagues from IAEA. And what you said about using this platform for collaboration, that's music to our ears. That's why AI for Good exists. And it was just so great to see so many people joining from all around the world. The great contributions from the panelists. Of course, the great job from Alina moderating this session. Thank you very much. And with that, I'd like to go through a few last housekeeping issues. First, I'll ask my colleague Bastien to put up a very quick survey. It's just one question. How likely are you to recommend this webinar to a friend or a colleague? Score of 1 to 10. I usually click on 10, but I leave the choice up to you. If you could quickly click on that. And in the meantime, I'll take you through some upcoming sessions in our calendar. And actually, tomorrow there's a session that might be quite relevant and interesting to many people who registered for today's session. Tomorrow there's a session on AI and energy transition. It's at 2 p.m. Geneva, European time. So if you're interested in this topic, it's quite likely that would be of interest to you as well. And I recommend you check it out. Also, before the holiday seasons are upon us, we have 16 more sessions on topics ranging from healthcare to climate to trust, machine learning and 5G, innovation factory startups. And I would recommend that you check out our website, aiforgood.itu.int, and check out our program, because we have 16 more sessions before the holidays. And of course, we already have many sessions planned for next year. So please take your time to browse our program. And with that, we've reached the end of our webinar. So just again, a big thank you to the speakers, the partners, all of our sponsors, and especially our co-convener, Switzerland. And I hope to see you all tomorrow. Thank you and good evening. Bye-bye.
Thank you and good evening. Bye.
Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector. Rewind selector. Rewind selector. Rewind selector. Rewind selector. Rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector,